Okay, now we want to start solving some exponential equations. And again, we'll have a couple of different techniques we use. Keep in mind we've solved a lot of equations, and already we've solved linear and quadratic, we've solved some rational equations and higher degree polynomial equations. So again, exponential is just going to be another type of equation that we can solve. Since it is a different type of equation, we would expect a different method to use. In general, I'm going to break it down into two kinds of exponential equations. So what I'll refer to as type 1, okay, are equations where each side of the equation can be written as a single exponential with a common base. Okay, now it doesn't happen very often, but when it does make the problem much easier than the other method. Okay. Now again, that's going to require us to just be comfortable looking at equations and trying to decide what base we could change each side into. Okay. But with numbers with bases like 2, 3, and 4, we should be able to pick out the common base fairly quickly. Okay, so just looking at a couple of quick examples before we get to type 2. We're going to rewrite each side as a common base. So when I see 25 to the x equals 125, these both should feel right away like powers of 5. Okay, I know 25 is 5 squared, and I know 125 is 5 cubed. So I'm going to change that 25 to a 5 squared, and this is still to the power x, and I'm going to change 125 to 5 cubed. Okay. Now again, I want to clean up this exponential on the left. Sorry. So this is power to a power, so we multiply. So I have 5 to the 2x equals 5 cubed. Okay. And again, the advantage is if you can have the left side be 5 to a power and the right side be 5 to a power, the only way these can be equal is if the exponents are equal. Okay. And so then it becomes a nice linear equation, x is 3/2, and we're done. So it is a nice method when we can use it. So it is worth checking. If you have an exponential equation, again, that means powers are up in the exponents, if you can solve it this way. Just a couple more examples. So I see a 1/2 and a 4. Those would both be power 2. And again, the right side's a little bit easier. 4 is obviously 2 squared. Remember, 1/2 is 2 to the -1. Again, we have to be a little bit more careful with negative exponents. But you should start getting used to the idea of fractions maybe resulting from negative exponents. So again, this would be -1 times x, which is negative x. It's 2 squared. So the only way these two sides can be equal, 2 to the negative x equal to 2 squared, is if the exponents are equal. And again, divide by -1, and I have my solution. Again, a real nice method, much easier than the other method we'll see. So when we can use it, we try to use it. Just a couple more, maybe less obvious ones. So I have 3 to the 5 minus x equals 1. It might not feel like those would be common bases, but remember 1 is a number to the 0 power. So if the left side is 3 to a power, I could write 1 as 3 to the 0. Okay. Keep in mind if the left side were 4 to a power, I could call 1 4 to the 0, and so on. So already then I have common bases. So 5 minus x is going to have to equal 0. Okay. Solve this, and I get x equal to 5. Okay. And then just one more, 32 and 16. Again, it might be tempting to think 4, because 16 is 4 squared, but remember 32 is not 4 to a power. Okay, so it's a little bit easier to call these both base 2. So remember 16 is 2 to the 4th. 32 is 2 to the 5th. And we have to clean up these exponents, but power to power we multiply. So that's 2 to the 5x. And then here, I'll just call it 4 times 1 minus x. Common base 2, so the exponents have to be equal to each other. Again, a nice linear equation, so I distribute and solve for x. And x is 4/9. Okay. So again, it's a nice method when it works. Obviously, if in this example this was a 31 or a 30 or a 33, this is not going to work, and we need another method to solve. We'll see in a second. Okay, so then type 2, right, is when each side cannot be written as powers of the same base. So again, you can see my examples here. I have a base 2 and a base 3. Okay, there's nothing I'm going to be able to do with that. Same thing here. I have a 7x. I have a minus 12. I have to add the other side, but it's not going to be written as a common base. Okay, so we'll have to be a little bit more careful here. These are a little bit more difficult to solve. Sometimes they're impossible to solve. Okay, but essentially what we try to do is isolate an exponential. Some of these have more than one, so at least we'll just try to isolate one of them. And then we're going to apply a logarithm to both sides, because that'll allow us to use some log rules. Okay, now again, you could use any log we want. I will usually choose the natural logarithm, so I'll take the ln of each side. Okay, log base 10, the common logarithm is also used. Again, you can use any base you want, but typically we will use ln. So then our answer is left in terms of the natural logarithm. Okay. Again, this will help us get the variables out of the exponent, but then we're going to have to just sort of see what kind of equation we're left with. Okay. So in the first one, again, make sure that you isolate first. So we want to add this. Here's our exponential, so we have to add 12 to the other side. Okay. And again, clearly, the left side is base 7, the right side is 16. I can't write in any way with base 7. Okay. So I'm going to apply ln to each side. So I'm going to take ln, and again, just be careful that you take ln of the whole side. And you do it to both sides of the equation. Okay. Now this looks worse, so it doesn't look like this is helping us solve, but the reason we want to introduce an ln here, right, is because one of our log rules says ln of 7 to the x, we can bring that power down in front. Why is that nice? Well, because now this is a multiplication. I know how to solve. I know how to isolate x. If it's x times ln 7, I just have to divide. So again, the challenge for us is that the variable we're trying to solve for is stuck in the exponent. We have to get that out of the exponent. Well, if I introduce a log, I might be able to use one of my log rules. Okay. So I divide both sides by ln of 7. And x equals the ln of 16 over the ln of 7. Okay. Again, if you choose a different base for your log, your answer might look a little bit different, but will be equivalent. Okay. And then for this one, again, we have two exponentials. So the best I can hope for is at least they're both by themselves, they're isolated on each side. But as long as one is, I can try this, apply ln to each side. So ln of the left, ln of the right. Again, for right now it looks worse, okay, but the idea is I have ln of 2 to a power. That power, and again, just be careful, it's the whole power, can come down in front, and it would just be 3x plus 1 times ln of 2. And then similarly here, our log property says I can pull down that 4 minus x power times ln of 3. Okay, again, what worked well for us is that our x's, our variables, are out of the exponent. This is just a linear, right? I have x to the first power. I'm going to move the x's to the same side, and I should be able to solve fairly quickly. Okay, it looks a little messy when I have numbers not just like 3 and 1, but I have a number like ln of 2. But that is no problem. Okay, so I'll distribute first. You could divide first or whatever, but I'm going to distribute. I want to get rid of all my parentheses. So ln of 2 has to get distributed, right, and ln of 3. Okay. So I'm going to write it as 3x ln of 2 plus ln of 2 is 4 ln of 3 minus x ln of 3. Okay, but again, it's just a linear equation. So I'm going to move the x's to the same side, move the constant over, divide, and that should be done. Okay. So again, I'm going to move these two terms that have x's to the same side. So I'm going to add x ln of 3 over to the left side, and at the same time I think I'll move this ln of 2 constant over to the right. Okay. Now again, normally if these are like terms, we can't really add it, so we just factor out the x. So 3 ln of 2 plus ln of 3. Here you still have 4 ln of 3 minus ln of 2, and then divide by this coefficient. So you get 4 ln of 3 minus ln of 2 all over 3 ln of 2 plus ln of 3. It's not as nice an answer, but it's just a linear equation. We divide by that coefficient. X is by itself, and we're in good shape.